Hi, so thank you for coming. I'm going to talk about Nakamoto consensus from multiple resources, and this is a joint work with Christoph and my advisor, Christoph Ph.D. So what's our result? We characterize the design space of Nakamoto-like protocols operating in fully permissionless setting using physical resources that are secure against double spending attacks. Right. I will explain what these words means as we go along. So, okay, what are we doing? So the motivation is like the OG Bitcoin, which uses proof of work and operates by creating these blocks after solving some hash puzzle. And in case there's a fork or like an adversary is trying to do a double spend attack, like we see here, then we simply take the cumulative sum of the difficulties and choose the one which has a higher weight, right? This is called longest chain rule, but it's really heaviest chain rule, and then pick the one which is heavier in the weight. Okay, so we given a Bitcoin chain, right? We can plot the hash rate over time with each block, so we can see the resources from the block, and then we go to a more idealized setting where we think of this as like a continuous curve. So the process looks like something like this. So you have some actual resource, right? So the resource is shown in the top, and then from that you create a chain. From the chain you read off what is like sort of the resources that went into each block, and then that kind of gives you approximation of the chain profile, which is like some sort of approximation of the resource profile. So for honest parties, this would, like if there is an honest chain, like then everything would look, the resource profile and the chain profile would look the same. But if there's an adversary, it can do some other things. It might look different, right? So we'll see what that is. And the security assumption basically says that if honest parties have more resources at each point of time, then any adversary which tries to do a private double spending attack does not win, right? So it's secure against double spending. So to summarize, we have the abstraction that is fully permissionless. I think everyone here has an idea what permissionless is. Fully permissionless is a more technical definition. I will give an intuition about it in the next slide. Okay, Bitcoin uses proof of work, and the chain selection rule is the heaviest chain. So choose the chain with the highest cumulative weight. And the security against honest majority. So if honest proof of work is higher than the adversarial proof of work, then the chain is secure. So we represent in this talk like the proof of work with W. Okay, so honest W is greater than adversarial W. Fine. Now coming to the permissionlessness. So in this beautiful paper by Louis Pye and F. Carden called Permissionless Consensus, they defined various degrees of permissionlessness. So the most permissive setting is called fully permissionless, in which Bitcoin operates, where the protocol does not know anything about the current participation, right? And anybody can leave and join just about any point of time. A more restrictive setting is called dynamically available. So all proof of stake protocol have to be at least at this level or even more restrictive. In the interest of time, I'm not going to explain what these are. So there's like a quasi-permissionless, which usually PBFT quorum-based protocols operate in, and then you can finally go permissioned. But in this talk, we are just going to focus on permissionless setting, right? So from this point on, like just imagine everything to be in a fully permissionless setting. So another fully permissionless blockchain is Chia, which does not use proof of work, but instead uses proof of space and the VDFs, like verifiable delay functions. And then it combines them in a nice way that the weight at each point of time is the product of the space multiplied by the VDF speed, right? So you can see here in the graph, like we have the green is like the VDF speed, and say blue is the space, then we get this pink weight function, right? And again, it's very similar to these two things are similar to Bitcoin. And we again have a heaviest chain rule, which is to choose the chain with the highest cumulative weight, except that the weight here is S times V. And the security, again, comes from if we assume that the honest SV is greater than adversarial SV at each point of time, then we have security. So, okay, I think in the interest of time, I'm going to skip what proof of space is, but broadly, there is a cryptographic protocol to prove that you hold certain amount of space. And VDFs are like analog of, a verifiable analog of time lock puzzles. Okay. So we work here with three physical resources. One is work, which is essentially parallel computation. And we have the proof system, proof of works, to deal with it. And the units we measure in hash per seconds. Okay. And then we have velocity, or rather the VDF, which is sequential computation, where the proof system is verifiable delay function, and the unit is steps per second. And finally, we have space, which measures disk space with the proof of space as a proof system, and the units are in bit. Notice that the first two are units something x per second, right? And this will be important later. So we can classify our three physical resources, the only ones we consider in this work, along in certain groupings. First is this timed notion, right? Which are the work in VDF, which have the units which are in some x per second. Another is quantitative. So the work in space are quantitative in the sense like adding more amounts of work, or like rather more amounts of chips increases the work, right? So if you double the number of chips, you have twice the amount of hashing rate. And if you twice the amount of disk you have, then you have twice the amount of space. That is not true for VDF in the sense it's a qualitative resource. So only the quality matters, which is that the highest, the fastest VDF you have, right? If you have 2 of them or 3 of the chips, that doesn't matter. Okay. Okay. So, right. So the Nakamoto-like abstraction that we want to do is like, so I showed this picture before. So this is the idea that we have resource profile, somebody creates a chain, and from the on-chain, you can measure how much resources went into each point, and then you can get like a chain profile. So, so in our abstraction, we just think about like a resource profile. Okay, and how do you create a chain profile? Then from a chain profile, you can get the weight of the chain, and the heaviest chain selection rule will choose the one with the highest weight. And this weight function would take the chain profile at any point of time, give it some real value, and then we can just integrate over, right? So it's a natural extension to the whole weight. So the question we have that we answer in this paper is like, which weight functions, gamma of W, S, and V, are secure, right? So security here is just against the double spending attack. So we know that gamma of W equal to W, which is the Bitcoin one, is secure. And we also know that S times V, which is for the Chia, is secure. But what else, right? Like there could be arbitrarily many ways of, combining them a priori, right? Like, so this is kind of like the mathematical question. So we're gonna do a little game where you can try to guess which one is secure or not. Okay, so W secure, SV secure, but if we take 2 proof of works and simply add them up, is it secure? I guess you guessed it's secure. Well, fine. Okay, but what if we multiply them? Is it still secure? No. Funnily, no, it's not secure. Okay. Okay, what if we take the square root of the 2 product? I mean, I just said W1 times W2 is not secure, so what now? Well, it turns out it is secure. Okay. What if we take like a S time, like a analog of Chia, which is S times W, right? Instead of VDF, we replace it with proof of work. This is secure. What if we multiply VDF with work? Is it still secure? Nope. Again, we take a square root, and now we again become secure. Okay, so something funny is happening, right? S squared times V is insecure, and square root S times V is secure, but I will not get into those in this talk. I will suggest you look at the paper. Okay, so I mean, when I made you play this game, like it's a bit of cheating because I didn't tell you what adversary can actually do, right? So what adversary is essentially doing is lying about timestamp, because remember, this is a private double spend attack. So adversary is creating its own chain, and in a fully permissionless setting, we have no way of knowing what timestamp it puts, right? There's no. So what adversary does is, okay, so there are two things it can do in this idealized setting. So we have this curve, like this is, say, the real curve of what adversary actually has. It can simply stretch it, right? So pretend that as if it had it for the 6th unit of time. But then for work and VDF, these are like timed resources. So per second, it looks as if it has a little less than what it actually had. But the area of this curve does not change, right? Like, so it's still 12, 3 times 4 and 6 times 2. It could also squeeze them, so take a lot more time to create some blocks, so that looks like as if the block has a much higher weight, right? So again, like, yeah, so this is the squeezing of 4 units of time. You kind of squeeze it into 2. It appears as if you had 4 units for the 2 unit of time. But again, the area does not change, okay? So, okay, combining them, these two, like from the pink, you can get the purple. And now the question, okay, like, what do we do? What is interesting that space, this does not happen. If you stretch or squeeze the timestamps, the space you have remains the same. And this is a property of how proof of space works. Okay, but if you were to combine all three in like a single block or like a single chain, which is represented by multiple resources, how does it work? The only condition is that when you stretch or squeeze something, it applies to all three equivalently. So any interval of time you can squeeze or stretch, but it has to be done at the same time. But for different intervals of time, which are non-intersecting, you can apply different functions. Okay. Okay, there's an additional attack on space called replotting, but again, interest of time, I will not get into that. But it's one way of making space appear larger. So given adversarial capability, let's look at Bitcoin again, right? Like, so I said like it's secure. Okay, but why is it secure? Because the area does not change, right? Like you're gonna stretch and squeeze, you're gonna still get the same amount which you had before, so the total weight does not change. But let's see an insecure function, gamma W1 times W2. Okay, in this case, we had like let's say the honest resources are this, so you have like 1 going all the way to 8. I hope you can see that there are two distinct lines, like one purple and one green. So the total weight is 1 times 1 times 8, which is 8, right? But if you squeeze this, right, squeeze it to the half the time, so now the total, both the resources become twice. So, and the total weight then becomes 2 times 2 times 4, which is 16. And hence we got like a higher, the more weight. And this is what leads to the insecurity. Okay. Okay, so this was W1, W2. When we combine graph, we get this graph. But if you actually take the square root of this, we get back that the area in the both cases is the same. And this is the intuition for the result. So formally, weight function gamma of S, V, and W is secure if it is monotonically increasing, homogeneous in B and W, and subhomogeneous in S. So just to remind you, the function F is homogeneous in Y and Z if you multiply alpha with Y and Z, and we get the alpha outside as a factor, so alpha times F of X, Y, Z. And subhomogeneity is that, okay, if you multiply alpha inside the X, then you get like something that's less than equal to alpha of F of X. Okay. So monotonically increasing is a very natural condition that if an adversary has some resource and it uses less resources than what it has, then it should obviously be secure, right? And that's, we can also formalize this. And homogeneity was this idea of keeping the volume or the area under the curve same. And subhomogeneity comes from this replotting attack, which I didn't talk about it, and I suggest you you check out the paper for that. And we can generalize this result to any number of different proof of space, different VDFs, and different work, and we get like the analogous conditions. But you'll be asking like, okay, so what? Like, what's the big deal? Like, okay, as such, we got a much larger class of functions to pick from than what was known in the literature. What was known in literature was this W, S times V, and that you can add multiple proof of works, right? So let's say, this is not a formal thing, but for decentralization, suppose we want to take multiple proof of work and combine them, right? But how should you combine them? So our work gives like large class of functions to combine them. So I'll just show a few interesting one of them. So first is this, let's say we combine them by adding them and with some appropriate like constant factors. But then from a perspective of if you have some X amount of budget, like some X dollars you have and you want to invest, which one will you invest if you want to maximize the weight, right? You will simply invest in the cheaper one, like relative to modulo the constants, which is not what we wanted from the decentralization perspective. Let's try another one, which is this min of C of W1, C2 of W2. And this is a function I don't think anybody would usually propose. Like it only comes, we only saw this as a secure function once we got our characterization because it's homogeneous in W1, W2. So in this case, what's going to happen, you're going to invest in a way such that both the weights are actually equal. Still not what we want. The third one is the most interesting one, where we take the square root of W1, W2. Here, the dollar amount of investment in both W1 and W2 is going to be equal. And this does not matter what the price of W1, W2 is. And if the price changes over time, the equilibrium will actually shift. You will, again, move to a place where you could give equal investment in both. And this is somewhat inspired by automated market makers. Right. Concluding with some future work, we gave this more abstract, like idealized rules, but like how do we make it practical? That will be a question that's of interest. Further, something of interest is that one big thing that our work does not have is proof of stake, right? Proof of stake operate in dynamically available or quasi-permissionless setting, and we are in fully permissionless setting, but it will be interesting to see the landscape of heaviest chain rules in other settings as well by adding proof of stake. And the question that's most interesting to me is how do you design like a block reward mechanism for various rules, which will lead to better, like people have to contribute resources, right? How do you incentivize that in order to make some kind of decentralized notion from the, say, from the 3 rules I showed in the previous slide? With that, I'll conclude. Thank you.
Questions.
Hi, thanks for the talk. This is more of a follow-up on the second point. So maybe you could, as a future direction, analyze if I have a certain amount of money, how I should allocate it to whether purchasing the resource in the system or like staking it in the proof of stake variant. If you think of these two things being combined in the protocol to basically boost my power in that protocol. And it would be cool to see a model of how money should go into the staking versus how it should go into these resources.
Right.
Yeah.
That'll be definitely.
Thought about that?
We did, but it's that proof of stake like creates its own different kinds of attacks. Like we kind of emphasized on the physical attacks because they have some uniform set of attacks which you can do on them. Proof of stake, especially with this long range attacks and like buying old keys or something. So we didn't know how to model that. So maybe if we just like, okay, say that you are not allowed to do this attack, maybe the model can be clean, but then it's not complete. Like, so that was one of the issues, yeah.
So one question I have is for the 2 sources, W1, W2, you multiply them, take the root. So this is equal investment, but this sort of give you a total weight that is kind of comparable with both, right? Do you have considered, like how to maximize the resulting weight while still be equal investment?
Well, one way you can do it, like if you know that they have like some fixed price all the time, then you can choose the appropriate factor. So you can have W1 times 0.1, W2 times 0.9, right? As long as they sum up to 1. That will work, but the drawback is that if the prices change, then we don't know how it changes. And
so maybe you can prove that this square root multiplication is actually optimal. I don't know. I'm just guessing.
Yeah, I didn't think about it, but yeah, that's an interesting thing to look
Okay.
into. Yeah.
Okay, thank you. Let's thank the speaker again.